Hey everybody, GL1 here, and I wanted to show you some experimentation on different forms of energy. One is chemical energy, another is light energy, and another is kinetic energy converted to electrical energy. So, the first one I'm going to go over is light energy converting to electrical energy. And of course, we do that with solar panels, right? So, this solar panel here is at least 40 years old. I've been hanging on to it for a really long time, waiting for a use for it, and I really never had much of a use for it. But one of the lessons I've learned, and I've almost always followed it, is I don't throw away old electronics that might have a use later. And that, living by that axiom has actually been a really good thing. There's so many times where there's something I saved, and as long as I remember where it is, it ends up being useful to me eventually. And this is one of those things. So here we have a really old solar panel from either the early 80s or maybe even the late 70s. And we're going to see what kind of energy we can get out of it. Now, I have a multi-tester over here. And what a multi-tester does is it tests different levels of voltage. It tests resistance. It can test a thing called continuity, meaning is there even a connection between two things? And this one, we're going to do this experiment. It's set on DC, direct current voltage, which is what a battery is. And I have it set on 20 volts, so it'll read anything 20 volts and less. So to make sure it's working, I'm going to show you chemical energy. And that is in the form of a battery. And of course, everyone knows batteries. And this is a AA battery, and it should be around 1.5 volts. So we'll get our multi-tester here. So this is basically going to be kind of our control, because we know the battery should, unless it's dead, read a voltage. And there we go. It's 1.45 volts. All right, so we get 1.45 volts out of this battery. And they say 1.5 volts. This battery is not totally new, and it's not an alkaline. It's a super heavy duty. But, it doesn't really matter. I just wanted to have something as a control. And this is an example of chemical energy to voltage, right? 1.5 volts. And that's going to be important with our next experiment. All right, so let's see what happens with this old solar panel. So what we're going to do is we have a couple wires coming out of the solar panel. We have a black wire and a red wire with some green, striping on it. So that's our positive. The red with this green striping is the positive. And I have alligator clips hooked up to that. And I have a phone here with an LED light. So we have a consistent light source. And we're going to hook up the positive to the positive on the multi-tester. And we're going to hook up the negative alligator clip to that. And there we go. And we should be getting a voltage, and we do. We get 0.13 volts. Now, we're going to take this experiment a little bit further, and a little bit, I think, well, a lot of bit more interesting. All right, so how far is the solar panel from the light source? And it is about 14 centimeters, okay? So at 14 centimeters, we get 0.13 volts. So we're going to write that down. All right, so now we're going to raise this solar panel up to 4 centimeters away from the light source. Why 4? No reason. Just really, actually, the only logical reason in this case is because my clamp is about 4 centimeters high in order to hold the solar panel square. So, but no, other than that, it's kind of arbitrary. So, all right, 4 centimeters, and we get 0.26 volts. So we get double the volts. At 4 centimeters. So what does that tell us? It tells us that the closer we get to the light source, the more photons are hitting the solar panel. They're not getting diffused along the way. They're hitting the solar panel, and they are being converted to electricity. So one can also think of it as how strong a light source is. And I'll give you an example of that. See, this little solar toy here, this little car, has a solar panel on top. I've had this car for about 10 years, and it will not work indoors. I cannot use a light source from inside that's powerful enough, that hits the solar panel enough to get this little tiny motor. Let me show you. Actually, if you see any of the other STEAM classes, the little motors, actually the little motor on the space station, which actually I have over here, and you'll be seeing that. The space station, here, I'll just get that. Okay, the motors on the space station are the same size as the motor on this little car. And also, this motor is the same size as what you might get in a tiny little helicopter toy. So when you have a radio-controlled helicopter, that's about the size of the motor. So you can see there's the pinion gear, okay? And small to big is going to make torque. So it's going to, get a lot of torque. And we need, though, a powerful light source. So just so you know, so the more powerful the light, the more voltage you get. All right, so that's the kind of energy we can get out of this solar panel. So when we compare that to a battery, it's significantly less, right? We're like a volt and a quarter away, it's like 1.25, 1.23 volts away. So it really doesn't give us a whole lot of energy. You'd have to have 6 of these about in order to equal that battery. Okay? All right. So now we're going to go to another solar panel. And this solar panel here went to our solar solar system. So you see our solar system over here? Right there? Okay, so that's also one of my STEAM classes. You can take a look at that. So this is the solar panel for that. I removed it, and then it has these little screw connectors, and I took some wire and I just tamped them down on there, and I can get my voltage from those wires. So now we're going to hook up those alligator clips again. In this case, the white one is the negative. Here we go. All right. So let's see what kind of voltage. All right. So at 13 centimeters, we get 0.42 volts. So this is the solar, let's see, this is the solar system. Okay. And at 14 centimeters, we get 0.42 volts. Significantly more powerful than that really old solar cell, right? So one thing we can infer is that the technology, after 40 years at least, is better. So we get more, it's able to capture more voltage. All right, so we're going to move this up to 4 centimeters. And let's see what happens. Okay, so we get 0.51 volts. 0.5. Yeah, 0.5. Okay, so not a huge improvement. All right, so it didn't double. It went up about 20%. So we get 0.5. Yep, 0.5 volts. All right, so you would need about three of these solar cells to equal a AA battery. Now, it may be able to provide the voltage, but it is unlikely that it could provide the amperage. And what that means is if you had three of these cells, you could run something that runs on 1.5 volts that doesn't need a lot of power, like a small, really small motor, okay? But if it was a 1.5 volt AA battery can run, let's say I'd say a motor that's probably 4 times the size of what the solar panel can run. So even though it's the same voltage, it takes more electrons. They're all running at the same speed. Remember, if you remember the metaphor of people running in a pipe. So 1.5 volts is 1.5 volts, means these guys, let's say the electrons, all right, let's say they're people, electrons are people, they're all walking at 1.5 miles an hour, all right? So if you have 3 solar panels and you have a AA battery, they're all walking at the same speed. But the AA battery is going to have a lot more amperage. So you're going to have a lot more people walking at 1.5 miles an hour, all pushing, it's just like all these people. Let's say you have 1,000 people pushing a wall, that's on wheels at 1.5 miles an hour, where you might have only 10 people pushing that wall at 1.5 miles an hour. They won't be able to move it. So it's going to have to be a much smaller wall, much smaller motor. Okay, so that's one thing to know about solar panels. They might, even if they equal the voltage, they're not able to produce the same kind of amperage. And that's why solar panels are good for charging a battery over a long period of time. And then you can use that battery. It stores that amperage up over a long period of time. And then you use the battery to run the larger motor. Okay, and let's say that motor is generating electricity for your home. All right. So now we're going to go to the solar panel that runs a space station. All right. So now this one, I didn't want to do any damage to the wires. So it's a little difficult to get at, but I can do it. So what I have to do is I can't use the alligator clips on this. I have to use the pointy little prongs that are on my multi-tester. All right, there's a lot of wires here. Get everything out of the way. All right. And once I hit the right spot, I'll be able to read the voltage. Okay. So get our multi-tester here, and positive is on the left. And see that? I think you could see there's a little silver there. I can hit that and then hit that one. And then we get, at 14 centimeters, we are getting 1.22 volts. All right, so if you compare the size of this solar panel to this solar panel, it's not twice as big, but it's probably a good 35% bigger. So what do we get? 1.21. Let me double check that again before we write that down. Yep, 1.22 volts. All right, so we're going to this is our space station. And at 14 centimeters, we got 1.22 volts. So that is just about three times as many volts as we got from the solar solar system cell, and something like 8 or 9 times the amount of the old solar panel. All right, so let's move this guy up to 4 centimeters and see what we get. All right. There's not anything dangerous about this with the prongs, by the way. You can't get shocked. Again, the voltage coming out of here is very little, and you can't get shocked with these prongs. Now, if you were using this on a very high voltage or amperage, you have to really be careful. But in this case, it's safe. All right, so now we're getting 1.87 volts. So that's more than the battery, isn't it? So you could use this. Because it's actually more volts than the battery, you could charge the battery with this. You can't charge a battery efficiently with less voltage, but if you have a little bit more volts, and in this case you do, you can charge the battery. Now, it would take some time, but you could put this out in the sun, or actually you could put it underneath the cell phone. Now, the sun's going to hit this with a lot more power, and it's going to get more energy from that. But I believe our max was it 1.87? This shifted a little bit, and then it went down. So because you know what it is because the clamp is a little bit rounded. I mean, it's holding something rounded, and it's pinching it, making it slip a little bit. So, okay. So 1.9. All right, so 1.9 volts. All right, so we're going to say 1.9 at 4 centimeters. Okay. So I have one more thing as far as a solar panel to show you. All right. I snuck into Dr. Zornstein's laboratory, and he has this kit over here. This is the 160N1 electronics kit from 1982. So it's really old, and it has a solar panel on it. Now, this is a really different looking solar panel. It's very flat. You see that? It's very flat. And we're going to see what kind of voltage we can get out of this at 14 centimeters. So it has these spring connectors here. And one of them is positive and this one is negative. So we can just connect it right here. So that's 0.73 volts. Now that's an old solar panel. That is 41 years old. So what does that tell us? It's not necessarily the age. Not that much. The technology to produce a good solar panel existed 41 years ago. So let's say 0.73. Let's do that again. Yeah, 0.73. All right, so that's at 14 centimeters. Now, can we do this at 4 centimeters? Here's what we're going to do. I'm going to lock these into these springs. So what you do is you pinch it, all right? And then I'm going to have to manually move this downward. I'm going to have to unclip it to 4 centimeters. Okay, and now we are getting 1.81 volts. 1.81 volts. All right. So I would say this is rather amazing, isn't it? We have a solar panel that's 41 years old that's that's producing just almost as many volts as our new solar panel for our space station. And it's just been sitting here, and it's very flat, and it's a very different design. So that is really fascinating. But I have something else to show you. All right. What I'm going to show you is mechanical energy to voltage. So I have this very old, nasty looking flashlight, and it just broke. So, but not broke enough that it doesn't work. This here is a generator. There is a motor inside and a spring that's on this handle. So you squeeze this, you hear that? I'm turning a motor. There's a gear. Every time I move this in and out, I am moving a motor. That motor is hooked up to a rechargeable battery, and I am putting voltage inside that battery. And then it has an LED. I hit this button, and we get light. And then if we keep hitting it, you can see how it kind of bursts. It gets a little bit of a burst of a light. And because it broke, we can actually look inside and see how it's made. So the wire here holds this from falling too far out. All right, so if we pull this out carefully, do you see the gear? It's a vertical gear, right? It's just teeth, and this is moving in and out as I push it, and it's turning a motor. And the spring, see this spring? That sits inside this gear, and that pushes it back out. So I push it in, and it pushes it out. I push it in, it pushes it out, and every time I push it in, it is turning a gear that's attached to a motor. That is attached to, you see this, can you see that that's green inside there? That is a rechargeable battery. Actually, I think we can get some light on that. There we go. All right, you see that rechargeable battery in there? See the red wire? And there's a black wire right next to it. And that is several cells. It might be 3 or 4. They might be what's called N-size batteries. They might be a little smaller than that, but they're definitely close to N-size batteries if they're not. And so what happens is by pumping that in and out and turning the motor, the same way that a battery, the electricity from a battery turns a motor, and then, okay, so you have a battery that can go directly to, the chemical energy can go to mechanical energy and turn the motor. Well, if you use kinetic energy, your hand, to turn the motor attached to the battery, it puts the electricity back into the battery. So the systems can go back and forth. So it's the same thing with, like, if you have a dam and you have water falling down the dam from one height going down the other, going down to a low area, and the water is falling and it's hitting a propeller, right, which we call a turbine. That turbine is attached to a motor. That motor is spinning. When the water spins the motor, it generates electricity. The electricity then goes to a rechargeable battery, and the electricity is stored in the battery, and then you can take the electricity out gradually to perform work, such as turn your lights on in your house. But I have one more example of this that's really neat that you may never have seen before. And this is a radio, and it has a flashlight. And for old cell phones, it used to be able to charge old cell phones. You could hook a USB up to there, and you push it over to cell phone charge, and it would charge the cell phone. Well, right now, this will run on regular batteries, but I have no regular batteries in there. I only have rechargeable battery cell in here. See this? So those are N-size batteries. All right. Now, watch this. So there's only battery in there is a rechargeable battery. This is from Radio Shack from quite a few years ago. It's a FM, AM, and shortwave radio. So you turn this. Now you see that red light coming on, it's charging. So the food I eat goes into my body and allows me to use my muscles to turn this crank. That's kinetic energy. And it's converting kinetic energy to electrical energy. And then I turn this.
Join the department that keeps one of the largest systems.
And then you can turn on a light. So that made the battery work, and then turn on the light. Now the light is probably going to burn it out pretty quick if it even has enough. You know what? Or it's not coming on, so it could be that the bulb is dead. Let's see. Or you know what? No. You know what it is? Is running out of energy. There we go. Okay, so if I turn the radio off and then I turn the crank, I can get light to come out of it. See that? So I'm converting mechanical energy to electrical energy right there. All right, so I just think you thought that would be neat. All right, so what I'm going to do is I'm going to do an equation. I'm going to use these numbers here, and I'm going to see if I can figure out any kind of consistent ratio with these numbers, and then I will be getting back to you for the finale of this video. Okay, so I wasn't able to come up with any real meaningful ratios here, but what I can tell you is that there's a 20% difference in how well the old solar panel worked in comparison to the 160-in-1 solar panel. So you had, that's that ratio. And then you had the space station and the solar system had a 24% difference in its voltage capabilities. So the 160-in-1 and the as far as their efficiency, both were about half at the different distances, but you get a lot more voltage out of the old solar panel, and the old solar panel is very similar to the space station, but in terms of the drop-off, the loss of energy from 4 centimeters to 14 centimeters, the old one and both of the old ones were similar in the drop-off when they're further away. So that can tell us something, that the newer solar panels, all right, from the solar system and from the space station, they don't drop off as much in how much volts they produce depending on the distance. So, there's definitely, I would say, an improvement in capturing light. All right, so thanks for watching this experiment. Hope you learned something and enjoyed this, and I will be sneaking this back into Dr. Zornstein's laboratory, and I don't know what it is, but I have a feeling he's going to explain to you what all these wires mean.